When we picture scientific progress, we usually imagine a quiet laboratory. We picture someone holding a beaker or meticulously examining a few precious drops of a new compound in a glass pipette. But a few drops of a new antibiotic or an experimental clean fuel won't serve a global population of 8 billion people. To make a meaningful impact, that laboratory discovery needs to be manufactured by the millions of gallons. This animation shows exactly why scaling up is so difficult. You cannot simply take a laboratory recipe and multiply the ingredients by a million. When you drastically increase the volume of a chemical reaction, variables like heat dissipation and pressure shift unpredictably, frequently resulting in a violent failure. Bridging the gap between a tiny, successful lab experiment and massive, safe industrial production is an entirely separate discipline. This is the exact domain of the chemical engineer. A discovery in a lab provides the blueprint, but without the engineer to build the manufacturing infrastructure, those instructions remain stranded on the lab bench. In 1928, Alexander Fleming discovered penicillin by observing how a certain mold killed bacteria in a small petri dish. The mold produced a miraculous antibiotic, but Fleming struggled to cultivate more than trace amounts. While he proved the medical concept, he had no practical way to produce enough doses to treat severe infections across the world. That required Margaret Hutchinson Rousseau. She designed the first commercial deep-tank fermentation plant, building a system that allowed the sensitive mold to thrive in massive vats, turning a scarce medical curiosity into a widely available, life-saving drug. Around the same era, industrial chemist Fritz Haber figured out how to synthesize ammonia for fertilizer, but it was Carl Bosch who scaled the process into towering high-pressure reactors, a feat of engineering that ultimately fed a rapidly expanding global population. A chemist proves what is possible. The engineer builds the machinery that puts that possibility into the hands of billions. Today, building that infrastructure involves operating sprawling industrial complexes. Operating these facilities means mastering extreme variables. Chemical engineers must precisely control the fluid dynamics of caustic liquids and manage the massive heat transfer generated by continuous, high-volume reactions. Manipulating these forces carries intense risk. A single failure in pressure management or cooling can release toxic gases or trigger explosions that threaten both the public and the surrounding environment. Because of this, chemical engineers function as high-level risk managers. They operate under a strict code of ethics, placing public safety and environmental protection above production quotas. This animated scale illustrates a core industry concept known as ALARP, which stands for as low as reasonably practical. Engineers use this rigorous standard to constantly weigh the heavy demands of mass production against strict safety thresholds, ensuring risks are minimized to the absolute limit. While the final output might be a plastic resin or a vaccine, the engineer's true responsibility is the safe, highly controlled system that keeps those chemicals contained and the surrounding community secure. For decades, these systems were largely associated with traditional fossil fuel refineries and the mass production of plastics. Now, the profession is pivoting towards the defining challenge of the 21st century: climate change. This flowchart visualizes one of their primary tools: carbon capture and storage. Instead of letting greenhouse gases escape, engineers design mechanisms to isolate carbon dioxide directly from industrial exhaust streams and securely compress it into deep storage blocks. They are also optimizing the complex thermal and biological processes needed to extract usable bioenergy from organic waste, working to make alternative fuels as efficient and affordable as gasoline. And as wind and solar power expand, engineers are building massive battery energy storage systems, ensuring that power remains stable even when the wind stops blowing or the sun goes down. Decarbonizing the global economy requires replacing the entire energy foundation of the modern world. That massive undertaking is a chemical engineering scale-up problem. To manage a transition of this magnitude, the field is integrating artificial intelligence into its physical infrastructure. Machine learning algorithms can now process millions of data points from sensors across a facility, allowing engineers to adjust temperature, flow, and chemical mixtures in real time for maximum efficiency. This integration enables predictive maintenance. AI systems monitor the microscopic wear and tear on valves and pipes, predicting catastrophic equipment failures and allowing engineers to replace parts long before a leak occurs. The next time you take a life-saving prescription or turn on a light powered by a solar grid, consider the vast hidden architecture that made it possible. A brilliant chemist might discover the blueprint for the future. A chemical engineer actually builds it at a scale that can save the world.